Hello. I got this a couple problems for you two students. I think it was Brandon and Kyla. I think they were Kayla. And this one I think Kayla wanted, and this one was kind of what Brandon wanted. So I decided to put them both in the same thing and upload it to YouTube and send you guys the link, and so you can see what's going on. The problems are very similar. This one's a little bit more complicated simply because there's three definitions of the functions, where this one's only defined twice. Okay, so the first one, f of x equals 3x plus 1 if x is less than -1, and -2 if x is greater than equal to -1. Now, this one right here is its own individual function. It's a y equals 3x plus 1. So if you have 3x plus 1, that graph is a diagonal line with slope 3 and a y-intercept of 1. Now, that's what it is as long as its x is less than -1. So it's only going to be that line. So it's kind of like a half of a line, if you will. So it's going to have a starting point. And the starting point is -1. And what I do when I do these things, I look at these boundaries. I call these boundaries because this is where it changes over. And some teachers don't like this, but I like doing it. It's not because I think it gets confusing with a vertical asymptote, and that's something totally different. But this is kind of like the boundary line. And what this is basically saying is the graph is y equals 3x plus 1 as long as x is less than -1, which means to the left. So I put y equals 3x plus 1 on that side. And on the other side, it's -2. And so y equals -2 on this side of -1, and the other side it's y equals 3x plus 1. So that's why they call it a piecewise defined function, because it's basically multiple pieces. This one over here will have 3 pieces. This one only has 2. So y equals -2, if you remember, is a horizontal line. And it's a horizontal line down here at -2. So it looks like this. Notice I started here at -1 though. And it's only because the x's, the inputs, are greater than -1. So if you're to the right of a number, you're greater than. So x is greater than -1. The outputs are -2. Now on the other side, it's y equals 3x plus 1. And that's a line. And what I like doing is finding a point on that side and using the slope to find me another point. So over here at -2, which is defined because x is less than -1, I'll see what it looks like at that point. So I put -2 back in. 3 times -2 is -6 plus 1 is -5. So -3, -4, -5. So it's a little bit in my spot there. So I'm going to bring this down a little bit. So at -2, my output was -5, which is about right there. And then using the slope of y equals 3x plus 1. Remember, I'm just graphing. All I'm doing is I'm graphing 3x plus 1. So up 3 from there and over 1, which is right there, which happens to be the same point. And so it goes like this. So these two pieces sometimes match. I'm going to show you when I show you this one over here, they're not going to match up. But this one I wanted to put on. I wanted to show you that the two pieces actually join. There's still multiple pieces. They just join at the same point. They don't have to do that, and I'll show that over here. And so what happens is at this point right here, the -2 says it's greater than or equal to -1, so it's a solid point. And then the line y equals 3x plus 1, it doesn't include the point, so it's a hollow point. But as everybody knows, if you fill in a hollow point with a solid point, it's become solid. So this is what it looks like. There are multiple pieces here. They just join. The multiple pieces join. So on the left side, it's y equals 3x plus 1, and on the other side, y equals -2. So if you treated these separately, and this is not the answer, by the way, this is the answer right here. If you treated these separately, this is what it looks like. Y equals 3x plus 1 has a y-intercept of 1, has a slope of 3, and it looks something like this. So y equals 3x plus 1 looks like that. Y equals -2 looks like this. Okay, so that's y equals -2, and that's y equals 3x plus 1. You can't just simply put them both on the same coordinate plane, because then they'd overlap, and if they overlap, they would not be a function. Vertical line test would fail. But what's really going on here is on this y equals 3x plus 1, at negative 1 is the magical cutting off point. So at negative 1, you erase everything to the right, and that's where this comes from. And at y equals negative 1 on this one, which is the magic boundary point, you erase everything to the left because it's only defined greater than negative 1, and that's where this part comes from. See? So basically, you're just basically merging these graphs into the same place, and then fluff away, get away where it's not defined. So the 3x plus 1 part was removed to the right of negative 1, and that's what comes up. And negative 2 is defined everywhere, but if you say I'm going to restrict it only greater, then you take this fluff off. And then put this graph and this graph together becomes 1. So that's how piecewise defined functions are. It's defined to be one thing at one part of its domain and something else on the other part of its domain. But when you put them together, it's one whole function. So, and this one's kind of the same thing, but this time there's 2 boundary points. So there's, because if you notice, the negative 4 this way, it's x squared between negative 2 and 2, and 6 is going to be at only greater than 2. So boundary points are going to be at negative 2, just like over here it was at negative 1, and at 2. So in between the negative 2 and 2, it's going to be x squared. So it's y equals x squared in the middle. So that's a parabola. And to the left of negative 2, it tells me x. So this is important. This tells me where it's defined. So when x is less than negative 2, it's negative 4. And that's going to look very similar to that in y equals negative 2, just only a little lower. So 1, 2, 3, 4. So at negative 4, it's going to be a horizontal line, but you don't make a mark. See, it's just negative 4, but your mark starts there and goes this way. Why? Because it's only defined for the x values that are less on the left side of negative 2. And if you're on the right side of positive 2, you're at y equals 6. So over here, it's up here at 6. 1, 2, 3, 4, 5, 6. So it's 6, it's a horizontal line that way. So notice, horizontal line this way, horizontal line that way. This one's higher. How come? Because it says it's 6 at x greater than 2, so it's up higher. And then if you're less than negative 2, it's a little lower. And then what about in between? Well, it's the parabola, y equals x squared. It's between negative 2 and 2. So that's how important this is. So yeah, well, how do you graph a parabola? Well, that's part of the content we've talked about. And here I would just say plot a few points between negative 2 and 2. Put 0 in, 0 squared is 0. Plug in 1, 1 squared is 1. Put in negative 1, negative 1 squared is also 1. Put in 2, 2 squared is 4, so it's right there. And right there for negative 2. So it looks like this. It's like a bowl kind of a thing. Missed it a little bit, but that's okay. Now, that's what that looks like. So if you notice, though, there are 3 pieces to the graph. So 1, 2, 3, and they don't join like this one over here did. Okay, these join, but these don't join, but these do. So they can, they may or may not be known if they just happen to. Most of the time, they don't actually join. Most of the time, they are separate pieces. I wanted to do it on this one just so to show you guys that sometimes it does happen. Sometimes when this happens, people kind of get crazy on me. They say, this can't happen because it's supposed to be in pieces. Well, the pieces, if anybody knows that if you have 2 pieces of stick, you can actually put them together and make it look like one stick. And that's what's going on here. Now, the only thing is you got to make sure you put the hollow points and the solid points where they belong. It's only 6 if x is greater than 2, not equal to 2, which basically means at the 2 itself, it doesn't equal 6. So you can put a hollow point there, and that tells the reader that that point is not defined. Why not? Because it's defined here. That's where the solid point goes. You know, why can't you just put a solid point in both places? Because it fails the vertical line test. If you put a solid point in both places just to kind of cover your bases, you're actually doing more harm than good, because then it fails the vertical line test. Then it wouldn't even be a function at all. So, and you got to make sure you don't extend these too far, because if you extend these things too far and they look like they overlap, then again, it would fail the vertical line test. That's why I put the dotted lines there to remind you, don't extend it to this. That's like a wall, stop there. And some teachers will count points off if you put the dotted line there. So I tell my students in my classroom to just remove the dotted lines, okay, for the final exam. I don't count off on my test, but on the final exam, I would take those off because some people count off. And it's not a major count off. They usually count off a point, but point here and point there can add up after a while. So, and this point's a solid point as well, because it's defined between -2 and 2 inclusive. So the bars underneath this means it includes them. And for x less than -2, it's -4. So, yep, that's a hollow point down there too, because we want to pass the vertical line test. So, but anyway, that's 2 problems. And could you extend it even more and make it 4 pieces? You bet you can. So usually in this class, 2 or 3, usually 2. 2 is usually what we have. 3 is actually put on by some teachers who want to make sure that students get this down pretty good. So, and that would be me. So, but anyway, so that's it. I hope it helps you out. And I'm gonna, like I said, I'm gonna upload this to YouTube and send you the link, and hope it'll help you. Thank you.